All right, good morning, good afternoon, good evening. Whenever you're watching this, I hope you're doing well, you're staying healthy, and staying caught up with your work. Now, last class I wasn't here because I wasn't feeling too well, and obviously we are not on campus now. And when I read some of you came to talk to me. I read some of your emails, including the one from the sub. From what I gather, is there was a little bit of confusion about the solubility product constant and the common ion effect, especially with the POGO activity that I asked you to work on. So the purpose of this screencast is maybe to clarify a few things and then to get you set off on some other resources that you can use to maybe better understand this. All right. So I do have a Google slide presentation, and I had to export this as a PDF, so I can't click through it as I normally would, but I will provide this slide deck on Google Classroom. So when you have a chance, please check there. All right. So let's just start, and I've got to scroll down. So here's the first slide, and I'm just going to show all the points at once. All right. So the equilibrium constant is calculated just like we did all the equilibrium expressions prior to this, right? And this involves a precipitation or dissolution of a slightly soluble ionic solid. So slightly soluble, because we know if it's really soluble, these things are going to dissociate right away. But when it's slightly soluble, maybe some of these solid particles will not dissociate and they will stay together. Now, you've seen these equilibrium expressions written before, and the second bullet point just lists another dissociation kind of process. And you can see that here, this is a heterogeneous process. Hetero because all the species that are in this process are in different phases. We can see that the M sub P X sub Q is in a solid phase, right? So that's going to be our ionic solid. Now, when that's put into an aqueous environment, then those ions, the cation ions and the anions, are going to dissociate. And that's what is shown in that first generic chemical equation. Now, we can write a solubility product expression as shown in the last bullet point, right? And if you notice, we're only showing those ions that have dissociated, right? Now, why is that? Well, if you remember from the class that I was here, that things like solids and pure liquids, they're not going to change their concentration. And when we're looking at equilibrium expressions, we're only interested in the species that will be changing concentration or partial pressure. We're not going to talk about partial pressure here because it's really not relevant. So because of that, we're only looking at the products, in this case, the ions that are formed. Now, moving on, you might have got this from some of the ChemQuest worksheets that you've worked on, but we can look at this solubility product constant, and if it's a quantity, if it's a magnitude, a number greater than 1, then we know that this is going to be a soluble salt. If it's less than 1, then the salt that we're interested in, this ionic compound, is not going to be considered very soluble. Now, when the solubility product constant is actually less than the reaction quotient, then we know that there's going to be a precipitation of this salt, right? When current conditions, which is what Q is saying, right? Current conditions say there's a lot of product right now. And the equilibrium expression, the solubility product constant, is saying, you know what, at equilibrium, we're not going to have that much product. So because of that, that equilibrium, if we think of Le Chatelier's principle, is going to shift, right? The system wants to restore equilibrium again. So how's it going to do that? Well, those dissociated ions will shift back to form the solid, and you're going to get a precipitate that's formed. Now, this will happen until the reaction quotient is equal to the solubility product constant. Equilibrium is reached, and then the system's a little more stable, right? Now, this is an example of a practice problem, and because I can't, walk through this as a presentation, you can see the problem is written in a gray, and the solution itself is written down there in red. So what I would encourage you to do is maybe pause the video right here, read and work through the problem, and see if you can follow the logic behind the solution. And then once you have that, maybe resume the video. Now, the solubility product constant relates to the common ion effect, and this is what your POGL activity was all about. So this is saying, okay, how is the equilibrium of a system going to be affected when there's a common ion already in that solution? So if you're dissolving a salt, but the solution itself already has one of the components of the salt in it, how much is that salt, that ionic solid, really going to dissolve? So we know if the several salts are present in a system, they're all going to ionize, right? And if those salts contain a common cation or a common anion, then they're going to contribute to the concentration of the common ion within that solution. So for example, that last bullet point says, okay, you've got some sodium chloride and some potassium chloride that are dissolved in the same solution. Well, the two cations, the sodium and the potassium, they're obviously two different species, right? But they both share that chloride ion. So that's going to be the common ion in this situation, in this scenario. And that's actually going to affect how much of the salts will dissolve. Now, there is a nice simulation that I found that shows you how this works, and you can manipulate both the insoluble salts and the soluble salts, and you can see how we can set up these ice tables, like right down below that image, to see what the solubility of the insoluble salt will be. Now, as you're working through this, I would recommend that maybe you go to the Google slide presentation, again, provided in Google Classroom. Click on this link, either the image or in the notes section. I have the link below, and you can manipulate that, and you can kind of get a better feel for what's going on here, and maybe this will help you when you're solving some of the problems. Now, if there is a common ion, then we know the solubility of the salt will be reduced when there's already that ion dissolved in the solution, right? And it's important to note that when you add this common ion to a system at equilibrium, this will affect the equilibrium composition. It's going to affect what's in the system itself, but it will not affect the ionization constant. That is, the salts themselves are still going to ionize at a certain, I don't want to say rate, but they're going to ionize in a certain way, and that won't be affected. It's just what's in that system at equilibrium. Now, you have to understand the common ion effect both from a qualitative perspective and a quantitative perspective. And I mentioned, I think, just a little bit ago about Le Chatelier's principle. So we know that if we have a system that's already at equilibrium and somehow there's a stress or disturbance to that system, then that system is going to adjust to try to restore equilibrium again. So if a common ion is added, if we have a solution that has an ion, we're dissolving a salt, and one of the cations or anions is in common with what's already in that solution, then that system has to shift, right? That equilibrium will shift towards the reactants. Because there's so many of those common ions in there, we're going to get the formation of more of the salts again. It's going to shift back to the solid and a precipitate will form. Now, from Le Chatelier's perspective, this qualitative perspective, I hope it makes sense. And remember, I gave you that infographic from Compound Chem that you should look at. That's a really, really great resource. You should know that inside and out. Hopefully it makes sense there. But you're not just expected to know this from a qualitative perspective. In fact, you also have to know it from a quantitative perspective. So what I would encourage you to do is maybe, again, pause the video here, read the example problem that's posted, try to solve it on your own, and then when you're done, or if you're struggling, go back and look at the solution here that's in red. Hopefully this will show how not only qualitatively, but quantitatively, we can kind of illustrate this common ion effect. Now, after this, I have just a few more practice problems, 2, 3, 4, so 3 exactly. So what I would recommend again is going back to Google Classroom, opening this slide deck, opening this in presentation mode and clicking through this, get to the problem, and then try to solve it on your own before looking at the solution. Once you've done that, hopefully you start to have a little bit better understanding, and then what I would encourage you to do is go back to the common ion effect on solubility POGL. You should all have hard copies, and if not, I believe there's a PDF posted in Google Classroom. you should go through that and try to solve all the problems again. One thing I do want to note, though, and this is, I think, one of the problems that maybe you confronted when you were working on this, and I'm going to move this to this practice problem 2. So we can use the quadratic formula to solve some of these problems, but sometimes when we write these equilibria expressions, the quadratic formula won't work. Or sometimes we don't even have to resort to using the quadratic formula, right? Now, from AP Chemistry, College Board, you shouldn't have to go beyond the quadratic formula. Now, if you do, then you know that there's another alternative solution to that. So what you have to do here is consider, and I'm going through practice problem 2. I know I just said try to solve these on your own, but I just remembered this. So if we look at this KSP, the solubility product constant, it's really small, right? And when I mean really small, if you look at the initial concentration of the magnesium, right? Of this magnesium chloride solution, it's 0.10 molar, right? So that means there's going to be 0.10 molar concentration of the magnesium ion. Now that's really large compared to the solubility product constant. So large that any change is probably not going to have a big effect on the equilibrium concentration. So if it's really large, and what I mean by it, again, if that concentration of the ion is really large compared to the solubility product constant, the KSP, then we can pretty much say, okay, we're going to say this change in initial concentration in equilibrium concentration is going to be, it says, negligible. It's really not going to matter. And because of that, we can simplify the expression, right? And you can see in this example for in the solution, okay, we have a quadratic formula that's set up, and we could just employ that, right? But since KSP is so small, we can just rewrite the expression to be in a little bit simpler form, and we can solve for the solubility product constant in a much easier, much simpler way. Now, I know that you probably want a hard and fast rule about, well, what exactly is small, right? What's the cutoff? The cutoff is usually about 5%. So if the concentration is less than 5%, and let me rephrase that just to us so I'm clear. If that KSP value is less than 5% of the total concentration of the ion you're interested in, then we can say, okay, this change in the initial and equilibrium concentration is going to be negligible, right? When we're looking at molarity, and we're looking at exponents of 10 to the negative 12, 10 to the negative 20, 10 to the negative 30, then it's a pretty safe assumption, and we have to look at the molarity, but it's a pretty safe assumption that based on the question that you're provided, that the change is going to be so small that it's negligible. So hopefully that kind of helps, and hopefully when you look at the key for the POGO, which I also posted on Google Classroom, that you will see why in Model 1, why some of those equilibrium expressions were simplified. Again, they're simplified because the change is going to be negligible, and then we don't have to get into this more advanced, I guess, algebraic thinking. All right, so I hope this was helpful. If you have questions, I'll try to be responsive on email or Google Classroom, or maybe we can set up some kind of office hours depending on how long, through Zoom, depending on how long this goes on. So I would recommend that you set up Zoom if you haven't done so already, and I will send you links to that on Google Classroom for the next warm-up. All right, so take care, stay healthy, and hopefully I'll see all of you soon. Bye.